For today, Data Communications and Network 1 class, this is lecture 23rd. Okay, this is chapter 12, part 2, the Internet Protocol. We will continue with the TCP protocol. So last time we finished over here. Okay, we finished over here. Okay, about the TCP segment, okay? And today we will talk about the window size in TCP. To understand how the window size is used, okay, we will show an example of data transfer between station A and B, okay? And we show only the window instruction from B to A, okay? So we show how B control the flow. In order to simplify the diagram, okay, so we show only B control the flow from A, okay? We didn't show the that A control the flow from B, okay? Anyway, so this is kind of A send information and B send information to B. So at first, okay, A has on the blanket on the left, you will see that there's the number 5001 to 8000. That is the window, okay? The byte of the data inside of the window that can be transmitted, okay? So A send first, okay? A send the data with the send sequence number 5001, okay? This is like the byte number, okay? And they send from 5001 to 6000, so send for 1000 byte, and send the acknowledgement of ACK 349. The 349, this is the next expecting byte, okay? So this acknowledgement told B that A has received correctly up to byte number 348, okay? And is expecting the byte number 349. So since A expecting the byte number 349, okay? So B send the send sequence number 349, right, to A, and it sent from byte number 349 to 540, okay, so kind of short frame, okay, and then it sent acknowledge at 6001. 6001, this is the byte number, okay, so B told A that it has received correctly up to byte number 6000 and is expecting the byte number 6001, okay, and then it set the window size to 3000. So as I told you before, in this example, only B will control the flow, okay, to simplify the diagram. So the window size, so B set the window size to 3000. So right now, A has received X6001, right? So the window can start from byte number 6001, okay? And the window size is set to 3000, sorry, to 3000. So it's from 6001 to 9000. This is the byte inside of the transmitting window of A that can be transmitted at this time, okay? A send next A send the send sequence number 6001, okay, and send for 2000 bytes, okay, so 6001 to 8000, and then it's sent at 541 because it have received from B, right, 349 to 540. So if everything is correct, okay, there's nothing wrong. So A send acknowledgement of the next byte that it is expecting. So it's at 541. Okay. Then B send has nothing else to send to A. So B just send at 8001, okay, because A has received byte 6001 to 8000, okay, so it have received them correctly, and it's expecting byte number 8001. So it send at 8001 and set the window size to 700. You can see that this B tried to control the flow, right? Because at first it set the window size of 3000, but then now it's reduced the window size to 700. However, the transmitting window of A, okay, is previously is 6001 to 9000, okay? So you cannot reduce this. You cannot, you can reduce the window size from 3,000, okay, to lower. However, since you have permitted up to the byte 9,000 already, you still have to allow up to 9,000, okay? So the 8,001 is because, let me show you here. Okay. Okay, at this point, it's allowed up to 9,000 already, right? So when the window is 700, okay, and it's at 8,001, so you can move, okay, because of this, you can move the window to start at 8,001, right? However, if it's 700 byte, okay, with the window, it has to go to just 8,700, right? But because you have allowed up to 9,000 before, you still have to keep up to 9,000, okay? So that is the window of the TCP, okay? Now, if B send again, okay, B haven't received anything from A yet, so B send again, so B send at 8,001, okay? Now it's increased the window size up to 3,000. Then you can change the window, okay, from 8,001 plus, 3,000 for 3,000 byte, okay? So it's up to 11,000, okay? So this is a transmitting window of A that can be transmitting without getting any acknowledgement back, okay? You know the sliding window flow control, right? It's the same idea as a sliding window flow control. However, the sequence number is number of bytes and not the number of frame, just that, okay? So after A got this, okay, and the window size 3,000. Oh, okay, before going to that, we cannot reduce this one to below 9,000, okay? Even though we set the window that is only 700, because when you have allowed up to 9,000 already, the 9,000, the byte here, maybe is during the transmission, okay? Because what is in the window is allowed to be transmitted, okay, without getting acknowledgement back, okay? So this byte in the window may be still in the transmission, okay? So if you reduce this one to lower than what you have permitted before, you will have a problem, okay? You have a confusion. So that's why you have to keep it the same as what you have allowed before. Anyway, at this point, you send now the A sends sequence number 8,001, okay, up to 8,800, okay, so about 800 bytes, okay, so 800 bytes, and it's still at 541 because we haven't sent anything to A again, okay, so it's still at 541, sorry, okay, and after that, since the window, okay, there's still byte in the window, so we can send again 8,801, okay, up to 9,900. So it can set up until 11,000, okay, before getting acknowledgement back. So this is still at the same thing, okay. When we have received this correctly, we add 9,901 because this means that we have received correctly up to by 9,900, okay, and it sets the window size to 3,000, okay. So that's why start with 9,900, okay, and the length is 3,000 bytes based on the window size here. Okay, 3,000 bytes inside of the window. So that's why the window is from 9,901 to 12,900. This is what I was explaining before, that the permission that has been given cannot be taken back, okay? And this is because the byte, that is inside of the window may already be on the way to B, so you cannot take the permission back. Now let's look at the next topic, is establishing and termination of a transport connection, okay? to have a transport connection, to set up a transport connection, you need to do the three-way handshake, okay? Not only two-way, but the three-way handshake. What is a three-way handshake? Like you're greeting 3 times, okay? In this case, A send to B first, okay? So A send to do the synchronization, okay? And then send the sequence number X. X is a random number, so A pick a random number and then send to B. So send sequence number X, okay? Just any random number that A pick. And then B send the same, okay, like sync, okay, with the send sequence number Y. Y is also a random number that B pick. So it's a different number, okay? So send sequence number Y. And then acknowledge number X plus 1. As I told you before, when you acknowledge, you have to acknowledge the next frame or the next byte, okay? And so B send, when it's B send number X plus 1, then A will know that B has received that sequence number X, okay? Because X is just a random number. So if B haven't received it, B hasn't received it, B cannot send the correct number back, okay? So if A have received this, A will send number Y plus 1, okay? Again, Y is a random number that B picked. So if when B receive number Y plus 1, B know that A have received the handshake, okay, or from B, okay, to get the correct number to transmit back. So it has to be the three-way transmission, and sometimes this have to be done, okay, for a while, okay. So it's like it's not easy to establish this connection for a non-reliable network, okay, because before you have a TCP, the transmission is still unreliable, okay, but you have the TCP protocol in order to establish the reliability for the transmission, okay. Now, this is what I told you, okay. So A will send the handshake signal, which is SYN here, and B will receive it and accept the connection, okay. Then when A received back from B, it will acknowledge the message, okay. This is a three-way handshake. And after the establishment of the connection, then station A can transfer the data to station B, okay. And as I told you before, this is not trivial because it may be sent many times before you can get the connection, okay. And when you want to terminate, in this case, you don't have to do the three-way handshake, okay. Suppose A want to terminate, it will send the fin or finish command, okay, with the sequence number X to B, which is the same random number, okay, that you sent to establish the connection at first, okay. And then B will send number X plus 1 to A, okay, to confirm the termination, but A doesn't have to return again, okay. So that's just two-way for the termination. Next topic, we'll talk about the IPv4 and IPv6, okay. IP is Internet Protocol, okay. It's kind of a datagram protocol, and the Internet Protocol or IP is provide the best effort service, okay, with no guarantee. So you can think of this as when you send unregistered mail, okay, through the to the mailman, to the post office, okay. So the post office or the mailman try to send every mail, okay, correctly to the correct address and on time, okay. However, if there's something wrong, okay, there's no guarantee. So so this is kind of, you cannot send anything like very, very important, okay. You cannot use this just the IP, okay, to send like very, very important information. In that case, you may in the mail for the post office, you may have to like register it, okay, right? Register mail so you know what happened to the mails. It's the same thing, okay? So IP is like unregistered mail. No guarantee, but try its best to transmit the data, okay? Now there are two versions of the IP, okay, IP protocol, which is version 4 and version 6. Version 4, current version is like, it has been used for a long time, okay? But right now, a lot of people has changed to version 6 already. So kind of, for Ghase University, the current version now is version 6, okay? So the version 6 was considered like a next generation IP. However, it has been used right now at Gesetsat University and in many places, okay, this year, 2016, okay. So anyway, in 2014, IPv4 is still most widely used for 96%, okay. However, it will be necessary, okay, to change to version 6, okay, as I will tell you why, okay. Anyway, the IP version 4 and version 6 is different, like in the header, okay, you can see the header are different, okay. The IP header of the version 4 consists of 20 to 60 bytes, okay, and including data, it can go to 65,536 bytes, okay. But IPv6 datagram, okay, it have at least the basic header is 40 octets or 40 bytes already. So you don't have like 20 byte version, okay. So you have 40 byte basic header of the IPv6, and you can have extension header, okay, which can so you can have like more or longer header if you want, or if it's not necessary, you can have only the basic header of the 40 bytes, okay. And then you have the transport level PDU. The transport level PDU is the protocol data unit, or just like think of it as like the information frame, information field or the data field, okay, of this header, okay. Now, if we compare, okay, version 4 and version 6, you can see that version 4 has like many fields in the header. Version 6 has fewer fields inside of the header. This is version 6, okay. So for the version 4, so you have the first field is the version, okay, and then they has the IHL, DS, ECN, okay, like total length, identification, flags, fragment offsets, okay, time to leave, protocol, and header is checksum, okay, and then source address, destination address, and then option and padding. Okay, let's see what is omitted, okay, in the version 6, okay. Source address and destination address are still, this field are necessary, okay, so they are still in version 6, okay, but you can see that it is much longer source address and destination address. The version 6 has the next header, okay, which indicate whether there is any extra header following, okay, and IPv6 use hop limit to compare to the IPv4 that use time to leave. Time to leave is like how long you're going to stay inside of the network, okay. Hop limit is like how many hop you will go, okay, before you get discarded, okay. And then they have the length and, okay, the detail of this. I will not go into the detail of this, but I will try to compare them, okay. So the white field are kept, okay, so these are kept, the white field are kept from version 4 and version 6. The green one is the name of the position that is changed in version 6, the dark green, okay. But the blue-green is the one that is not kept or thrown away. So option and padding was thrown away. Header checksum is not included. Fragment offset, flag, identification, IDL, IHL, okay. And then there's the green, which is for label. That is the new field in the IPv6, okay. Now let's look at some of the main fields. The identification, what is this? In the version 4, okay, this is kind of an ID, okay, of the datagram. So if you use this with the source and destination address, okay, and the user protocol, so then you can uniquely identify this datagram. So you look at the datagram, okay, this comes from source B to source to destination E with the ID of this number, okay, and the user protocol, this user protocol, then you know that this is different from other datagram from the same user, or from the other pair of users. Okay, so this is the identification field. The fragment offset, okay, the datagram may be a fragment, okay. Again, this is in the version 4 only, okay. So the datagram may be offset, okay, you can see like this. This is the fragment offset here. The datagram may be fragment, okay, when passing through different networks in order to fit in the network frame size, or to be an E here, frame size. Okay, so in different networks, they have different limit, okay, on the size of the packet that it can send. So if you have a like long packet, okay, and at first, and then you go through some of the smaller limit, okay, in size, network that have lower size limit, okay, then you have to fragment it, okay. Now when the fragmentation occurs, each of the small unit will have the IP header, okay, which has a minimum of 20 bytes. This is again in the IPv4, okay. So they have the IP header are the same for every datagram, okay. And all of the small units also will have the same ID, but different fragmentation offset. So you know that it comes from the original, the same datagram, okay? So the same IP header, the same ID, but different offset. You see that like where it is, the offset is to indicate where in the current datagram this fragment belongs to. So look at the first picture on the left. It should be again IP header, okay? IP header is the same, okay? And this one is the first part that was fragmented, okay? So this fragment offset is number 0 because start from byte number 0 up to, in this case, up to byte number 3999, okay? And this is the IP datagram that has been fragmented. The second IP datagram from the original, the same datagram that has been fragmented into 2, okay? The second one has fragment offset equal to 4000 because the first one ends at number 3999, right? So this one starts at 4000. So from byte 4000 to byte number 7999, okay? So the same IP address, the same identification inside ID, okay, inside of the header, okay, but different offset. Because this is it's the different fragment, okay, from the original datagram. So to receive it correctly, to receive the datagram correctly, all of the fragments have to arrive at the destination before timeout, okay, and then they can reassemble into the original datagram, okay, and get the data back. But if you get, suppose it's fragmented into 5 parts, okay, but you get only 4 of them, okay, so maybe this one is missing, the second one is missing, then you will throw away the whole, you will discard the other fragments too, okay, because it's not the complete IP datagram. Now let's look at the next header of the IPv6, okay. In this case, okay, this field tell us whether there is any additional extension headers or not, because the IPv6, the number of fields are much fewer, okay, than the IPv4, because most of the time you just need this kind of fields, okay, like not many fields. However, in some cases, if you need some specific field, then you will add it as an extension of the header, okay. So if this header is the last IP header, the next header field, okay, the next header, okay, the field of the next header will tell us, okay, whether the transport protocol is, like, for example, if it's TCP or if it's UDP. So if you look at this, okay, the next header field, okay, so if you have next header, extension header, then it will identify that header, the optional header. But if it is the last one, then you will tell whether it's like TCP or UDP that is used in the transport protocol, okay. Now let's look at the IP address format. Okay, this is version 4. The IP version 4 address format. Okay, there are 5 classes. Okay, the class A, class B, class C, class D, and class E. Okay, for class A, the class A will start with the number 0. Okay, the first bit is number 0. This is the address format of IPv4. And then the next 7 bits is the network number. And the next 24 bits are the host number. So the total is 32 bits for the address. Now for class B, okay, it will start with 10. And the first 2 bits is 10, and then it has the network of network number of 14 bits, okay, and the host number of 16 bits. For class C, start with 111. The network numbers consists of 21 bits, and the host number consists of 8 bits. Okay. For class C, we use for multi-class. Okay. Transmission, which is start with 1110. Okay. For class E, okay, this is for future use. Okay, so we haven't used this. So we will basically focus on class A, B, and C. Okay, this is the address that you usually see. For class C, like multi-class, is like you send to many people. Okay. So the address field in IP header, okay, as I said, is 32 bits. Okay, for source address and 32 bits for destination address. Okay, so this consists of 32 bits, whether it's class A or B or C. Okay, it's all 32 bits. And this is a global internet address, which means that no one in the world can have the same internet address as this device or this user. Okay, so when you look at the internet address, you know where it is in the world. I mean, where it belongs to, which network it belongs to. It has a host identifier and the network identifier, as I say, is the network number and the host number. So we can call it like identifier of the host and the network. Okay, you have many class of the address format to make it flexible. Okay, and you have a lot of like different of network size, and they can be in the internet. Okay, so you can have like small networks connect to big networks. Okay, usually use only one class in the same environment. Okay, so for example, if you have a company and you have many lands, maybe the land for this building, the land for another building, or okay, so then you want to use like kind of the same class of the address. Okay, if you are like the same company. The 3 main network classes, class A, B, and C. Okay, for class A, you can see that there is only 7 bits for the network identifier, if you remember. So in this one, you don't have a lot of networks. Okay, because the first because this one, okay, 7 bits for the network identifier for class A. Okay, so you have only 126 networks. Okay, number. This is the maximum because like the 0 is reserved. Okay, so this one. Okay, but this is a very big network. Okay. So 7 bits is actually 128. However, 2 of them are reserved. Okay, so 126 network numbers are allowed to use, and this is very big network because you have a lot of a large number of bits for the host number. Okay, which is, if you look at this, you have host number of 24 bits. So 2 to the 24 possible users. Okay. And how to know that this is class A is begin with binary 0 in the address. Okay, so the network, as I told you, the network address, the first one all 0 and all 1. Okay, from the second bit. Okay, second bit to the 8th bit. Okay, all 0 and all 1s, they are reserved, not to use. Okay, and in this case, if you write the address in terms of the dotted decimal, it will start with 1 to 26. Okay, so this to 1 to 126. This indicate that it is class A address. For class B, this is a medium number of the networks because it has longer bits for the network, okay? It has 14 bits for network, okay? And it has 16 bits for host identifier, okay? So 2 to the 14 is the number of networks that you can have, and 2 to the 16 is the number of hosts that you can have in each of the network, okay? For class A, each network can have 2 to the 24 number of hosts. Okay. Now, class B begin with 1, 0, okay? And if it start with 1, 0, okay, the first 8 bits have to be 1, 0 and all 0, right? Which is 128 up to 1, 0 and then all 1, okay? In this case, it's 191, okay? So when you write in the decimal, dotted decimal format, okay, is the first number has to be 128 or to 191. You know that this is class B, okay? And so the second octet is also the part of the class B address for the network, okay? And you have so you have 2 to the 14 class B addresses, which means that you have this many possible network in class B, okay, in the world, okay? Now for class C, you have a lot of networks, right? Because the first 3 bytes are for networks identifier, but only the last byte is for host identifier. This case it starts with 110. So 110 and all 0 is 192 in decimal. 110 and 101 is 223 in decimals, okay? So the address, the dotted decimal address of the IPv4 is 192 dot, xxx, okay, and to 223 and dot x, okay. So in this case, the first 3 octets are the part of the network address, and so you have 2 to the 21 or about 2 million address. So you have about 2 million network possible for class C, okay. But each of the network has 2 to the 8, which is only 256, okay, 2 to the 8. So 256 users, okay, for each of the network in class C. Okay. Now we'll talk about the subnet and subnet mask, okay. Usually, okay, we want to assign a single network number to all of the LANs as a site. So if for เกษตรศาสตร์ okay, maybe we want like one network number, or for a company, we want the same network number that go to the company, even though they may have many LANs inside of the company or inside of เกษตรศาสตร์, okay. So for the rest of the internet, okay, when people outside, okay, look at เกษตรศาสตร์ at บางเขน, okay, or look at a company, okay, they want to it look like only a single network, okay, at the site. So when they want to do the routing, addressing, and they look at this address, they know, they say เกษตรศาสตร์, okay, บางเขน. So you send the mail like to เกษตรศาสตร์, right, or send the packet to เกษตรศาสตร์. And then inside of the เกษตรศาสตร์ University, they would have someone, okay, or a method to distribute the message, okay, or the mail or the packet, okay. Suppose it's from the post office, okay, say เกษตรศาสตร์ บางเขน send to เกษตรศาสตร์ บางเขน, and then someone will sort it, okay. This one go to Faculty of Engineering, this one go to Faculties of Science, this one go to another faculties, this one to graduate school, something like that. So we will do it inside of in your own network, okay. So for outside people, they will think of it as like only one address, okay. This is the same. So inside we will have kind of a sub-network. So the big network is like เกษตรศาสตร์, and the sub-network is for like faculties, different faculties, for example. So you can have like many LANs inside of the one network, okay. So if you want to allow the routers, okay, to work easily, okay, to do it correctly, to route the packet correctly. So each of the land will assign a subnet number. So it's like, this one, go to เกษตรศาสตร์ university, right, in the mail, okay. And then faculty of engineering, okay, so go send to faculty of engineering. And then the faculty of engineering may send to department of electrical engineering, something like that. So this is kind of the subnet. But usually we use only one level of the subnetwork, okay. So in this case, the host identifier part, okay, in the address of the IPv4 is partitioned into a subnet number and a host number, okay. So you have kind of another level of addressing. So this is like the address of class A, class B, class C, and then in the host part, you divide it into the subnet number and the host number, okay. So by using the subnet and by using the subnet mask, the address mask, the subnet mask, okay, we allow the host to know, okay, whether this go to this LAN, okay. As I say, you look at it, okay. This is go to graduate school, so you know that you have to route this way, something like that, okay. That doesn't have to know inside of the grad school. They will do it by themselves, okay, again, to send to the correct user, okay. So in this case, let's look at examples, okay, of the subnet mask and the address. For the IP address, okay, you can see that if you have the IP address in the binary format, okay, there will be 8 numbers followed by a dot, okay, followed by 8 numbers and followed by a dot, and then another 8 numbers, a dot, and another 8 numbers, and the numbers are in binary, okay, and then you have the corresponding dotted decimal number. So the dotted decimal number, they are basically okay, this is that. This is my sheet, okay, so okay, this is the IP address, okay, in binary format. So 8, okay, 8, okay, and then each of the 8 bits, okay, are represented by a decimal number. So 110, and then 00000 is 192, okay, the first number in decimal format, okay. And because it started with 110, you know that this is class C. This is class C address, okay. And you can also look at the 192 and you know that this is class C address, okay. Then the next 8 numbers is 111000100, okay. So you convert it into decimal, okay. Decimal is 228. The next one is 00010001, okay. This is 17, and the last 8 bits, okay, is 57, okay. So just don't worry about this line, okay. Look at this as this number is 8 bits is converted to 57, okay. Now if you have a subnet mask of all ones here and then 5 zeros in the end, okay. So this is for the class C. The host is the host address 8 bits, right? Host address, the host host identifier is 8 bits. So in the 8 bits, okay, because you have a mask here, the mask is all 1, okay, and also 3 bits here as a mask, and then all 0 here, okay. Then when you do the bitwise AND, okay, of these two, you will see that you will get the result, okay, as what? You do the AND. When you do the AND, if it's 1, okay, if the mask is one set of number is all ones, when you AND something, you get that's something, okay, the same thing. But if the mask is 0, okay, when you AND something, you get all zeros, okay. So the first part here, this part is all 1, right? So the whole thing here go down to this. This is the same as this. Okay, because this is marks. Marks is the first part is all 1. So this is the same as this part. The first line and the third line are exactly the same. However, when the marks is all 0 here, you see that the resulting and will be all 0. Okay, will be all 0 because and 0 and something is just zeros. Okay. So you see that this tells you the marks. The marks of 3 bits tell you the subnet number. The subnet number here is 1. Okay, because the first 3 set of binaries are the network identifier, and the host is the last 8 bits. Okay, so in the past of the last 8 bits, the first 3 bits here is the subnet number, and the last 5 bits here is the host identifier. Okay, so in this case, the subnet number is number 1. And what is the host? The host number is the rest of 5 bits. Okay, at the end, 11001, which is 25. Okay, so in this case, you have subnet number, host number, okay, and class C address. Okay. Now let's look at another example. The default subnet mask. Okay, if it's a class D, if it's a class A means that the data is the network identifier is in the first 8 bits. Okay, and the last 3 bytes. Okay, are the host address. So the default mask is 8. The first one in the 8 bits. And the examples, okay, of class C masks of class A masks that we are using is, okay, the first one are all 1, but this one we can have 2 bits here. Okay, so this part is host, right? The last 3 is are host, are the host identifier, and this one tell you the subnet, okay, the number of subnet. So in this case, you have the subnet, okay, 2 bits is the subnet, okay, and then the rest is the host number, okay, and in the dotted decimal, okay, for the class A default mask is 255.0.0.0. For the example of the mask is 255.192, because this is 1, 1 and all 0, right? You convert to decimal is 192, okay, and .0.0. Now if you look at class B mask, okay, the class B mask is all 1 here for 16 bits, okay, and then all 0 for the last 16 bits. So 255.0.0. Let's look at the examples, okay, of class B mask. So this is the host part. The host part is here, and these are the part of the subnet. So you have 5 bits as the subnet, and the host is 16, 17, 18, 19, and 19 bits as the host number. Okay. In this case, you can see that the first number is 255. The second number, the third number is 11111 and 000, which is 248. Okay, and then zeros. In this case, you have 5-bit subnet, and then 19-bit 5-bit subnet. Okay, and 19 bits host number. Okay. The last one, okay, class C default mask is again here 1 for the 3 bytes, okay, and the last byte is 0. Okay, so this is the default mask. Dotted this one is 255.255.255.0. Okay, and if you look at example of class C mask, these examples, you can see that the host is the last 8 bit, right? The last 8 bit is the host. In this case, 6 bits is the subnet, okay? And 2 bit is the actual host number. So this is 255, 255, 255, and 252. Okay, so this is the dotted decimal for the class C mask. Okay, now let's look at an examples. Okay. Consider the number, the address number, okay, in the dotted decimal format like this, 197.200.135.79, okay, and the marks is 255, 255, 255.248, okay. What is 248? Okay, 248 is equal to 111110000, so 5 bits. Okay, so in this case, what is 79? 79 is converted to binary as 01001111. Okay, so you know that the first 5 bits, okay, is the subnet number. So the first 5 bits here, subnet number. This is the host number. So host number 7, right? What is the subnet number? 1001 is 9. So subnet number 9, host number 7 in this case. And this is the network. Because this is class C, right? One start with 197 is class C. So this part is the network identifier of class C. Okay, and this is inside of the company that you have 5 bits subnet. So you can have 2 to the 5 equal to 32 subnetwork. Okay, and each of the subnetwork can have 8 hosts. Okay, basically. Now let's look at another examples. $204, 108, 35, 40, and the mass is 255, 255, 255, 224. Okay. What is 224? 224 equal to 1110000. So you have 3 bit subnet. Okay, so what is 40? 40 equal to 00101. Sorry, you have 3 bit as a subnet. 001, 01000. So the first 3 bits, okay, is a subnet. So this is subnet number 1. The last 5 bit is the host. So host number 8. Okay, again this is class C address, and there are 8 possible subnetwork inside of this company, okay, or in this organization, and you have 2 to the 5 or 32 hosts for each of the network. Okay, now another examples. Let's look at class A now. This is the IPv4. This is 120, so you know that this is class A. Okay, class A address for the IPv4. And what is the mask? The mask is 255.248.0.0. Okay. 248, we have done it before. For 248 is 5 bit mask. Okay, 5 bit mask, submask. Sorry, 5 bit subnet. So what is this? Class A means that these are all the hosts. Okay, these are all the host number. So What is 24? 24 is 0, 0, 0, 1, 1, 0, 0, 0. And you know that this is 5 bits subnet. Okay, so you know that this is a subnet number 3. Okay, and what is the host? The host is, so this is dot 192, right? Over here. And dot 0. Okay, since this is start with 0, 0, 0. Okay, so the number here is host number, sorry, so this is the host number, the last 16 bit with the host number is from here to here. Okay, so this consists of 3 plus, so this is 19 bits host number. Okay, so you have to calculate because this can have like many hosts. Okay, but the subnet number is number 3. Okay. Now we will look at another examples. Okay, if you have something like this. Okay. Okay, so you have the rest of the internet, okay, sending the data, okay, or the datagram, okay, through the, for example, เกษตรศาสตร์ University. So you have a router here, okay, that receives that check like if this is the address for เกษตรศาสตร์บางเขน okay, send into this network, okay. But if it's not, then it will not. It knows that it's not for this company or this organization. Okay. So when it's received with this router, then you will check. Okay, they're connected with LAN X, LAN Y, LAN Z. Okay. So the LAN X has the subnet number 1. Subnet number 1. Okay, because the number is 192. To 28.17.32. Okay, so this is the subnet ID. Okay, the subnet ID is number 1. So in this case, if this host, okay, this host has the number, the address of 192.228.17.33. Okay, this means that this is host number 1 because 33 equal to 32 plus 1. Okay, so host number 1. So this is host number 1 because the number that you have seen before, you will see that, like in this case, 40 is host number 8. Okay, if it's 41, this is going to be 01001, so it's host number 9. If it's 42, it's host number 10. Okay, so you can look at it like that. So for this for another host, okay, here, this is 192.228.17.57. So 57 means that this is 32 plus 25, right? This number. So the host number is number 25. Host number 25, this one in LAN X. Okay. Now for LAN Y, LAN Y has the subnet number of LAN Y has a subnet of 192.228.17 and 64. Okay, and this is subnet number 2. This is subnet number 2. Okay. Now, what is 32? Okay, 32 equal to in binary. Okay, x 2 to the 5, right? 5, 4, 3, 2, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is 32. Okay, 64 is this one. And so if 32 is 0, 0, 1 and all zeros, okay? 64 is 0, 1 and then all zeros. So if 32 equal to subnet number 32 equal to subnet number 1 and this one equal to subnet number 2, okay? It means that this is the subnet masks. So you have 3-bit subnet, okay? And then 5 bits host ID, host number, okay, or the host ID. So the whole LAN Y okay, LAN Y is as end with 64 and the subnet number 2, right? So if you have the address of 65 here, .65 here, it means that the host number is number 1 because 65 is 64 plus 1, okay? And you may have router inside of the organization. So you have another router here, router 2, okay, connected to LAN C. In this case, you have a subnet number of subnet number 3, okay, subnet number 3, subnet number 3, okay, and this is 96, okay, because 96 is 0, 1, 1, right, and then all 0. Okay, so this is equal to 96, okay, so the subnet number 3, and this is 96, okay, subnet number 3, and the SS if is .97, okay, it means that the host number 1, okay, if it's .100, then host number 4, something like that, okay, so that's that is how you read, okay, the address and understand the address of the IPv4 internet protocol, okay. So that's the end of these lectures, and we will continue in the next lecture for the address of the IP version 6. Thank you.